Welcome back. Today we begin Chapter 2, the idea of limits. And we want to look at two essential ideas, that is average velocity and instantaneous velocity. Average velocity is velocity over a certain period of time, where instantaneous velocity is the velocity at an instant. How fast is something going at one particular instant? And these have analogies with graphs. We'll see how average velocity is related to the slope of a secant line, and instantaneous velocity, that's like the slope of a tangent line. All right, let's get to it. Average velocity is defined as change in position over change in time. Here's an example. Suppose that a car passes mile markers at various times. You can see it starts at 1 o'clock, and then every half hour time goes by and ends at 3 o'clock. The mile markers that it passes at various times are also listed. You can see they increase, 50 up to 80, but then they also decrease, 80 back down to 50. So what is the average velocity from, say, 1 o'clock to 1:30? So from 1 to 1:30. Well, the change in position, it has increased by 10. It's increased 10 miles. But the increase in time, the change in time, has increased by half an hour. We'll call that 0.5 hours. So 10 divided by 0.5 is 20. And the units stay the same. Miles was on top, hours is on the bottom, so the answer is 20 miles per hour. And that's the rate. The average velocity from 1 to 1:30 was 20 miles per hour. What is the average velocity from 1 o'clock to 3 o'clock? So all the way from the beginning to the end. Well, how did the position change? The position actually didn't change at all, if you only look at the beginning and the end. So we have 0, but it took 2 hours. So the average rate of change, the average velocity, is actually 0 miles per hour. It seems a little strange, right? Because it did move. It increased its position, but then the position decreased, and on the balance of it all, it ended up going nowhere. So on average, its velocity was 0. And then the last question. What is the average velocity from 2:30 to 3 o'clock? So look at this. From 2:30 to 3, the position actually decreased 20 miles. That's why we have a negative. So it's important to see we can have a negative in there. Whereas the time increased by half an hour. So negative 20 divided by 0.5, negative 40 miles per hour. Position can be positive or negative, so our average velocity can be positive or negative. Time, which is in the denominator, we always think of that as a positive change. Okay, here's an example where we actually include a function, unlike that miles example. Let's suppose that the height of an object after t seconds is actually given by a function, s of t. Its position is 6t minus t squared feet. And the graph of it is shown here. So at time 0, it has height 0. It's on the ground. After 1 second, it is 5 feet in the air. After 2 seconds, it is 8 feet in the air. After 3 seconds, it is 9 feet in the air. And then it descends and comes back down. And at 6 seconds, comes back down to the ground again. So what is the average velocity of this object from time 1 to time 4? Another way of saying that, what is the average velocity over the interval from 1 to 4? And we figure change in position over change in time. Well, let's see, 1 to 4. There's the time change. And what about the position change? Well, it started off at s of 1, and it ended at s of 4. So the change in position, I can write that change in s, delta s, over change in time is s4 minus s1 over 4 minus 1. And you evaluate what that is, and the answer ends up being 1 foot per second. So on average, from time 1 to time 4, its height increased at a rate of 1 foot per second. And we can kind of see this by making a line that connects those 2 points. This line has slope 1. I go over 1 second and up 1 foot. Over 1 second, up 1 foot. Over 1 second, up 1 foot. So between those 2 moments in time, on average, it was going up 1 foot for every second of time. So 1 foot per second on average. And that's the slope of this line. The slope of that line is the average rate of change, the average velocity. How about the average velocity from time 1 to time 3? Time 1 to time 3. Or in other words, the average velocity over the interval from 1 to 3. So once again, let's figure out our change in position. I have s of 1, I have s of 3 up there, and so we figured this out. Change in position is going to be s of 3 minus s of 1 over 3 minus 1, so change in position over change in time. Work it out, it ends up being 2 feet per second. And once again, I connect the 2 points, and that line that I've just drawn has slope 2. If I go over 1 unit, it ends up going up 2. Over 1, up 2. So on average, this object rose at a rate of 2 feet per second over this time period from 1 to 3. So we've seen that average velocity corresponds to the slope of a secant line. So I take my function, s of t, I graph the whole function, there's a curve, and if I take 2 time units and I see where the points on the curve are for that for those time units, I get a line. Oh, let me talk about this word secant. A secant line is a line that goes through 2 points of a curve. So a point and a point, draw a straight line, that's a secant line. That's opposed to maybe the more familiar tangent line that just grazes a curve at 1 point. So tangent line versus a secant line. All right, well, we had fun, didn't we, looking at the average velocity from 1 to 4 and the average velocity from 1 to 3. And we could also find other average velocities. How about the average velocity from, we'll keep the 1 constant, 1 to 2, 1 to 1.7, 1 to 1.035, and on and on and on. We'd have a lot of fun doing all these calculations, but at some point we're going to get tired of this, and we're going to say, wouldn't it be nice just to find the average velocity from 1 to t? Make that right endpoint a variable. Then I'd have a formula that would give me the average velocity from 1 to t. So that's what we'll do next. What is the average velocity from t equals 1 to, well, just t? Let's leave that endpoint a variable. So we have a formula that gives us our average rate of change. So in this case now, my delta s over delta t, it just stays a variable, s of t. And the bottom number just stays a variable, it's just t. Well, I know what s of t is. It's 6t minus t squared. So 6t minus t squared minus 5, 5 is my s of 1, all divided by t minus 1. Now, we do a little bit of arithmetic. You don't have to worry about the details too much, but I can simplify that expression and end up with a formula. And that formula tells me the average rate of change over the interval from 1 to t. So for any t I choose, I can just plug it in right now and find the average rate of change. That's kind of powerful, isn't it? I don't have to do the one-by-one special cases anymore. So, for example, what is the average velocity of the object from time 1 to time 1.5? All I have to do is plug 1.5 into my newly discovered formula. Put in the 1.5 for t there, and there, do the math, and it ends up being 3.5. So 3.5, say, feet per second. What is the average velocity from t equals 1 to t equals 1.01? That's only 100th of a second later. So I can plug in the 1.01 in place of t, do the calculation, and it looks like 3.99 feet per second. And this average velocity over 100th of a second, well, that's such a short time interval. It's almost the instantaneous velocity, isn't it? I mean, I would imagine that the instantaneous velocity of the object actually at t equals 1 has to be pretty darn close to 3.99. But what happens if I try to plug in t equals 1 into the formula? I get 5 minus 1 times 1 minus 1 all over 1 minus 1, which is 0 divided by 0. And that is just weird. You can't do anything with that. 0 over 0 is undefined. And so here's the real mathematical problem that we struggle with, is that average velocity. Average velocity is easy to compute. That's what we've been doing this whole time. Average velocity is easy. But instantaneous velocity, that is much more challenging. So how do we actually compute it? I don't have a formula that I can just plug in a value. And that is where the idea of limits come in. So instantaneous velocity. This is where calculus really begins. Let's continue our same example. The height of an object after t seconds is s of t equals 6t minus t squared feet. Here's how we find the instantaneous velocity at time t equals 1. First, compute the average velocity on the interval from 1 to t. Okay, so we did that and we get our expression there. I can compute the average velocity. And next, we let t approach 1. We can't let t equal 1 because then I'd have a 0 in the denominator. But I let t approach 1 and see where the average velocity goes. As t approaches 1, we find that the average velocity approaches 4. So this expression in the circle, that average velocity, that value will approach the number 4 as the value for t gets really, really, really close to 1. That's the idea of a limit. We let the variable approach a number, and we look at the average rate of change and see what is that approaching. It turns out that instantaneous velocity corresponds to the slope of a tangent line, and I have a little online demonstration to show that. Okay, so here we go. Here is a graph of the same problem that we've been working with, s of t equals 6t minus t squared, and I can move the right endpoint of t. I can make t 4, and we can see I can calculate my average rate of change. Change in position over change in time is just 1, and if I bring that closer to 3, I get an average rate of change of 2. So those were the two calculations that we made before. Let me throw the secant line in there. So when t was 4, that secant line has slope 1. When t is 3, that secant line has slope 2. And now let's let t approach 1. And as t approaches 1, t gets closer and closer and closer to 1. What is the slope of that secant line approaching? So keep your eye on this number in the far right, 3.2307. That's going to change. Here, I'll sneak t closer and closer and closer and closer to 1. That number is getting closer and closer and closer to 4. When I get really, really super close, I get really, so I got to back up a little bit there. When t is really, really small, that slope is really close to 4. Now, unfortunately, I can't let the t actually equal 1, because then I'd have 0 over 0, everything disappears. So my goal is to figure out, as t approaches 1, what does that number become? And this secant line, here's kind of the real key. It's a secant line because it really does go through 2 points. That secant line turns into a tangent line. So the goal of finding an instantaneous rate of change is really the same goal as figuring out the slope of a tangent line. One is a real-world problem, finding an instantaneous velocity, and one is more of a mathematical problem, finding the slope of a tangent line. But really, they address the same problem, and they relate to each other back and forth. All right, so that's it for 2.1. 2.1 was the idea of limits, and we see this through average velocity and instantaneous velocity.